Good morning and welcome to the first of our panel discussions here at SMTAi. It's cleaning challenges in a changing world. Of course, continuous miniaturization, harsh environments, and the need for traceability all present challenges to those who are seeking to produce levels of cleanliness that meet or exceed IPC TM 650. I'm joined by a very distinguished panel to help to discuss some of these issues. To my extreme right, we have Mark McMean from STI Electronics. To his left, we have Mike Bixenman from Kaizen Corporation. And then to my immediate right here, we have Jason Keeping from Celestica. Welcome, gentlemen. I'm going to go straight in with the first question, which is automotive, of course, is the biggest challenge by volume. They're trying to pack more electronics into the car, but the car's not getting any bigger. So it's increasing miniaturization and more functionality. So how do cleanliness experts deal with the increasingly difficult environment?
Yeah, so automotive raises some unique challenges for cleaning, and especially for the electronics as it shrinks. Most importantly, these are being run in very harsh and very hot environments. So a lot above the standard industry that you would normally have. So just, standard industries would be any of your consumer products or any industrial products. But automotive is pretty unique because they're actually putting sensors and electronics down along the engine and along the wheel wells and things of that nature. So those temperatures now are exceeding 150 degrees C. Flux residues are struggling to stay encapsulated at that. So they have a problem in that with those heats, the organics of those flux residues now become the mobile medium for that. Even though it's in a very harsh and hot environment, now we have a medium in which we now can have the ionics are free to move and free to attack and free to align. So automotive has a unique thing. In that case, what happens a lot is they're trying to clean and then underfill and trying to solidify those areas around their electronics to prevent this things from going mobile, which is the organic structures after the soldering process. In that, automotive is having to go in and do special cleaning and then do special underfills. And those underfills are designed to keep all of that stuff completely locked and sealed around those electronics due to the environmental heat that's being produced, where it is, where it's being generated around the car, around the vehicle.
Do you think current flux chemistries are robust enough to meet some of these challenges?
Well, they're robust enough in the original state to get it. The real challenge is if you're using a no-clean, how to get a mechanism or the flux carrier system to lock down and handle those high heats. That is, how do you encapsulate it? So no-cleans are all about the after you form the correct solder joint, how do you lock that in shell, in a protective shell? Right. The challenge is that we're exceeding normal temperatures, and that's why those organics are then able to become the medium for the movement. Right. So that's the challenge that they have, and that's why in a lot of cases they use secondary encapsulants to be able to seal and the residues that are under there.
Right. So the coatings, obviously, you're talking about. Does anybody have anything else to add to that?
I guess as Mark was saying, is when you start looking at conformal coatings, that's where now they're looking at doing in these new technologies, hotter environments because of all the density that's being placed, but they also help to mitigate any moisture that would now go through and start activating with these ionics. So by having the cleaning done, but then also conformal coating as a secondary mechanism, you now start to help that mitigated.
Right. That's interesting.
Yeah, and I may add that in a harsh environment, when we think about water or moisture, it's a unique molecule that really causes a lot of problems. It allows you to mobilize and to carry contaminants that can remove or carry these metal oxides, and when that happens, you can start to create leakage currents, you can start to create electrochemical migration, which really starts to cause the failure mechanism to occur. So as what Mark and Jason just said, the real critical element is that cleanliness is a requirement, but the key is to lock those electronics to a point where when you're in a harsh environment, you don't allow that moisture to get in contact with areas that could prevent failure.
Right. So, talking about the conformal coatings to lock these things in, I mean, increasingly manufacturers are using plasma cleaning to create the right surface tension for the coating. But I mean, is plasma and aqueous cleaning mutually exclusive processes, or should manufacturers use one or the other?
So I think that's a very good question. And if you look at it, you have an assembly, and then you have ionics or residues that are on the card. You then do assembly cleaning. That will then remove those fluxes and residues. Mm-hmm. But if the board and the raw materials are not at the right surface energy values, either because of the higher temperatures or different components that are going to be designed for lower costs, you have now that variable that's there, which cleaning alone would not do. Now, if you were to look at doing plasma treatment to actually increase the surface energy, that will then allow the energies to be higher for conformal coating adhesion, but you still don't remove the ionics. So you'd have to look at the overall is, if I do plasma, I still need to do the cleaning to remove the ionics as well as increase the surface energy.
So essentially you need both. Would you agree with that, Mike?
It depends. It depends on where the electronics are going to be. In some cases, if the electronics are in areas, for example, the plasma cleaning gives you better adhesion for the conformal coating, and if you're in a very stable environment, you may not need cleaning. A no clean process may work just well, but it's when you get into those harsh environments that do give you access to different humidity levels, different levels of moisture. And specifically, when you start to see these devices where components are increasingly miniaturized, your electrical field increases. You have less distance to create leakage or intermittent failures. So, that's where you start to see cleaning come into play. Is when those conditions are such that you can't afford to leave those residues behind from a reliability standpoint.
Mark, you do a lot of high reliability assembly down at STI. I mean, are you using plasma treatment and aqueous cleaning?
Correct. Yeah. So, to step off of what Jason and Mike said, it really depends on the application and the environment that it's going into. So, both of them are extremely right. From an application standpoint, you have to decide, where your electronics is being placed and what the degree of risk is and what mitigation you're going to do. If you're building safety critical stuff or high rel, or there's a person that's requiring that type of protection from that type of electronics, then you're going to want to put in all the safeguards. So cleaning is very important to get the residues gone and get the ionics off and get as clean as possible. The plasma etch is very important because now what we want to do is we want to prep that surface so that we can get the best adhesion to the types of conformal coatings. And thus, that's why the decision should be that you need to look and see exactly how the application is being used, and do you have all the right processes in place that's going to mitigate all those risk factors. So I'm in full agreement. But it is true that if you've got a really critical situation, all of that needs to be done.
Right.
The other is if it's not as critical or it's not in as harsh an environment, now you can make the decision on at what level.
Sure.
But
yeah, I get it. So I'm going to move on to my next question, which I think we'll start with you, Mike. That is, ROSE testing has been largely discounted as a reliable, repeatable test methodology. What testing methodologies do you recommend manufacturers can use in-house?
Okay, well, it's a challenging question. If we step back for just a minute and talk about the ROSE testing, the ROSE testing is a simple test method, and it's a test method that assemblers can use, and it's easy to do. There's equipment that's designed that allow people to do it. The problem is that when we look at the different soldering materials that are out there today, and as we look at the type of components that are built on circuit cards, the residues that are most problematic, the ROSE method is just not a precise technique that can measure those accurately. So as you look at that problem, and over time, there are other techniques that are out there, such as ion chromatography, surface insulation resistance. Those techniques have been around for a long period of time. And there are failure analysis labs and labs out there that will run those techniques for you. The problem is that once you validate or qualify a process, people want to know, am I keeping my process in control? And there's a void today on the shop floor in able to do that, which has really challenged all of us to say, how can we do it better? And there are different techniques that are coming out. I was Mark had chaired or was the keynote at an IPC SMTAi cleaning and coating conference roughly 4 years ago, and he was working on a project to do that. And I'll let Mark talk a little bit more about some of the techniques that they have worked on and developed that allow people to look at the shop floor and to make an assessment, whether it's on process development or process control. And so, yes, the ROSE method is a method that can still be used for process control, but as a cleanliness verification, specifically on these highly dense substrates, it really is an obsolete technology.
Yeah, so 4 years ago, STI went down a path of trying to understand what is the void, because ROSE has some limitations. It's really designed only to test rosin fluxes. But as you know, the world has changed from rosin fluxes, and we have migrated into a lot more sophisticated flux chemistries and compounds. And that has triggered, what do we do on the floor to be able to monitor process changes and how do they impact the electronics? And for a long time, SIR has been that tool, the B52, the B24. Those types of vehicles have been run in labs to gain that insight. STI took it on as a challenge to our clients because our clients were struggling with that, and we started down a path of putting SIR onto the floor to let our process engineers be able to see when they make a change to reflow, or they make a change to spray pressures, or they want to change cleaning chemistries, okay? You need to be able to quantify and create objective evidence to show your prime contractors, or in some cases, if you're directly going to the government like the Air Force or the Army, you need to be able to show that my changes do not impact your reliability on the hardware that you're building. Right. So the tool that was missing in our estimation was an SIR tester that was able to be put on the floor and run on a daily basis by process engineers and quality engineers who truly impact your day-to-day quality, because they're the guys that are on the front line. Mm-hmm. And we have been able over time to show, and we're presenting papers on that, to show that you now have a tool that can be used to identify process changes, material choices, material choice interaction. So think about if I have an SMT flux and a selective solder flux, and they co-mix, right? Yep. Because our densities are getting smaller. How do you know that interaction is still safe on that electronics over time? The only way to do that is with the standard that is true to, goes back in time. SIR testing has been around, but that allows us to gather data both electro and chemically, the electrical data and the chemical reaction data in those most critical points, and thus we now can create data and objective evidence that supports why we do what we do on the production floor.
Right. Well,
I might add to that, Trevor, that when you think about someone on the production floor, one might look and say, well, they're not really educated to be able to use an instrument like that. Well, as we listened yesterday, we were listening to presentations on CFX and the smart factory. Today, the way a process can really be enabled is one, to design your test cards so that they are really compatible or mirror what it is an assembler is trying to do. And then secondly, as those data outputs come out, to be able to process the data, to do the analytics on the data, and to give people real-time values on what's going on in their process so that they can make an assessment. One of the areas that we're researching together is to see, can you make that assessment in a shorter period of time? And can you provide, just like yesterday they were showing, a red, yellow, green condition. Can you use a current process and make some of those assessments in a real-time area that somebody who's not really schooled in the art can understand and make decisions by?
So what do you mean? You mean like adding a traffic light system to a cleaning bath, so if it's drifting out of spec, it would go red, green, amber, red?
Yeah, so if you look at a tester out there today, these testers make data points and thousands of data points at very small periods of time. So the real key element is to process the data real time, and so that it can be processed and it can be seen, and it can be, I mean, you can access the data on any electronic device almost anywhere.
Okay, well, it's really interesting. I'm going to move on quickly to our last question because we're running out of time here, unfortunately. What are the current frontiers for cleanliness testing? What are the biggest challenges facing manufacturers of chemistry and manufacturers? We'll start with you, Jason.
All right, so I'll quickly add to what Mike was saying, which
Okay.
kind of leads into this question.
Yep.
There's a lot of tools that are out there, but a lot of people don't know when they do the process controls, how have they been validated? Because when you start looking at the test methods, there's dynamic, there's static, there's heated, there's regular room temperature. So as we look at these different fluxes, how they get those ionics off the cards to get the testing to see, are we in a red condition, are we in a yellow condition, are we in a green, that has to all be done at the same time.
Yeah.
Because without the right process control, all the validation, there's nothing that's being connected.
The biggest challenges for manufacturers in terms of for cleanliness testing, what do you think they are?
I would say the biggest challenge is, again, these very small, miniaturized, leadless and bottom terminated components. Even if you want to clean them, they're difficult to clean because you don't have a large standoff gap. The other problem is that as you lower the standoff gap, the flux itself increases under the body of the component. It can bridge the conductive paths. And so even though cleanliness is critically important, the ability to get to that soil and clean it is a challenge, which gets into the process and the equipment that's able to accomplish that task.
For companies that are assembling really high rel boards for military and these types of applications, have you got a recommended minimum height that these small devices have to have a standoff so that you have the ability to clean them?
Yeah, so there's testing still going on, but the problem is when you get to 2 mil and below, you have a real problem being able to get a chemistry and getting that molecule with the saponifier in it to be able to get small enough to get underneath there. Then you got to have impingement pressure and the force to be able to get up under there, and that becomes a problem. We do know that as we increase that height, then we get to 3 mil, and if we can get to 4 mil, because we have some plating that's being done, secondarily onto those parts to give us some lift. Mm-hmm. If we can get that into that 3 to 4 range, now we have a channel to be able to get our cleaning fluid up underneath there, and now we can get impingement forces necessary to do it. As you go down, it becomes even more critical and more difficult to get under, but it's that lift that everybody's trying to do.
Right.
So we're working on boards and design techniques that can be done to your board. Removing the solder mask in and around the pins, removing the solder mask underneath the part so that we can get some of the added Z-axis height to get up under those parts. Mm-hmm. So we're working on test coupons to show the designers that they can do things at the board level. At the component level, if you're in a real critical situation, if you'll just tin the parts, you'll get added lift, right? Because you're going to be adding to the Z-axis of that part. Yep. So we build a very critical part for the military. Cannot say what it is, but understand that particular part has a son or daughter on the end of it. We tin those QFN parts to give us the lift necessary to do the cleaning. Okay?
Interesting.
And that's the whole intention, because we know the criticality. If we can get up under there, we can clean it. Then we actually conformal coat and overmold it and things of that nature to give added protection, to give it the longevity at the system level. But the critical point is we're doing things secondarily to it to give us that risk mitigation, to give more safety margin into the design.
Yeah.
That is a big challenge that is facing all of us, not just the military world and the automotive world, but even industrial stuff has it.
Yeah. I mean, there really should be a set of guidelines for IPC level 1 size, height standoffs, and level 2 and level 3. Make life a bit more standardized and simple for all of us. Gentlemen, we're run out of time. I want to thank you all very much for joining us. It was a great debate. Mark McMean from STI Electronics, Mike Bixenman from Kaizen Corporation, and of course Jason Keeping from Celestica.
Thank you.
Thank you.
Thank you for joining us today.